Thank you. That's awesome. So yeah, as just mentioned, we are going to get started, and we're going to go beyond borders today. We'll explore how we are basically building a cloud platform for global deployments, which is written in Go. So we're both enabling Go global deployments, and it's written in Go. It's a total Go loop, and we'll dive right into it. To give you some context, I'm Yann. I'm the co-founder and CEO of a company called GoLab, and I basically spent the last 12 years building cloud service providers, mostly in France. So in 2011, I was building a cloud service provider called Outscale, which is still operating today. It's now called 3DS Outscale, and it was written in Python. And we were basically selling virtual machines, EC2-like virtual machines with the original goal to address the French market. Because at the time, AWS and GCP were not even existing in France and were not present in the country. In 2013, I joined something which became later Scaleway. And from engineering, I ended up leading the product. So if you're not familiar with Scaleway, it's also a cloud service provider. It's basically providing a set of services today. It started with BareMetal ARM servers. And it grew up into a complete cloud portfolio with managed Postgres, managed Kubernetes, and managed object storage. And it initially started in Python, and in 2017, basically we started making the shift to Golang. And we'll dive into a bit into this history of languages in the infrastructure space. And since 2021, we're building another cloud service provider called GoLab, which is also this time written in Golang. And if you look at my history, by 2030, I'll probably still be building a cloud service provider because it seems to be what I do. But I would guess it's maybe not going to be in Go because we already saw a lot of changes in the last 10 years, but we'll dive into it a bit later. Maybe one question here for all of you. Are you all professionally working in Go? Yes. Who is working in Golang? Okay, so half of the room. The other one is either interested or just not raising their hands. And who has necessary or DevOps background and is actively working on operating cloud infrastructure? Oh, okay, that's a fair share too. Half of the room is also actively involved in operating cloud services. So that's going to be interesting. And because we will dive on how we build it, basically. To give you an idea on how we will go, we'll start by basically going quickly over what we do and what's specific. We'll then go into the principle of going global and serverless, which is a key thing we are trying to bring. We'll look at the evolution of languages in the infrastructure space from Perl to Go. And we'll end up with a large chunk of the presentation being on how we actually build it. To put it simple, we're a cloud service provider. We allow developers to deploy full stack applications in minutes. And the key thing we are trying to do is to not ask you to have any specific cloud provider knowledge or skill set. So we're trying to make it so that you don't need to learn all the internals and even the infrastructure concepts. And we're basically doing this through container and native code continuous deployment. So you can either deploy a ready-to-use Docker container or a GitHub repository, which we will build. And we completely abstract infrastructure management for the end user. But today we'll look into how this is actually working. And two key things we are also focused on is basically improving performance with global deployments and making sure at the end of the day companies have sustainable engineering and cloud costs. So we let people deploy any app and Go app globally. So being it like web apps, it can be like a Django app in Python, or it can be Go microservices, APIs, written in, which are receiving gRPC calls, and we'll make sure this is all smoothly running. And we're also taking care of basically executing background workers, and we're providing serverless managed Postgres. So that's a key thing. And so the key promise for us is to allow you to go from a local deployment to a global deployment in minutes instead of months. So it's a few comments, and we'll actually do it right now to get started. So here we have an amazing terminal that you should all see, and it might be even better if it's bigger. We are on a fresh account. We have nothing ready, and we'll just like deploy an application in 6 locations worldwide. So we are going to deploy actually a Go app. This is it. So basically, what we are saying here is we're creating an app which is called Fast. We're using a GitHub repository which is public. You'll see it's a basic Hello app, Hello World app on github.com/go. We are using the main branch, and we are routing the traffic to the port 8000. And it's actually deployed in Paris, Frankfurt, Washington, San Francisco, Tokyo, and Singapore. So we'll do this. It's saying warning. It's deploying worldwide, but basically that's more or less it. And our app is going to be available on fast-golab.coyab.app. It's going to take like between 2 and 5 minutes to start, hopefully. And we'll actually do another one which is a bit more visual, and we'll circle back to these apps later to see what happens. So the other one is actually simply a Docker image, which is our demo app. It's written in Next.js, and it's more or less the same thing. And so the wireless connection seems to be working, so that's great. And the second one is going to be available on global-golab.coyab.app. So if you go to this URL right now, you'll see 404, probably branded 404, and in about like 2 minutes, I think you'll see something. If we check our list, it's actually starting. So while this is happening, and they are actually, that's a control panel, we'll get back to it later, but it's actually deploying. While this is all deploying across continents, we'll dive into a bit why we believe it matters to deploy globally and what we call serverless, because it's not necessarily what you might believe. So first thing here is why we believe it matters to deploy globally. The key thing is about physics. The reason why people want to deploy globally is because data only moves at the speed of light. I mean, that's really the limit here that we are facing. And so what we are usually trying to improve is performance to improve user experience. And the classical challenges you'll face when deploying globally are regulations, being like GDPR or data locality constraints for specific industries. And actually in this data locality, you also have a subject of performance between your database and your application. Because if you deploy your application globally, but if your database is in one single location, it might even impair performance. And the rest of the challenge are technical. It's how you coordinate like continuous deployment worldwide and how you deal with global networking. And we'll dive into how we actually do it. The second key concept I want to highlight is serverless. There is a bunch of misconceptions. We believe it's not functions. I mean, it's not anymore because the term serverless was popularized by AWS with Lambda, which was function and which is still functions. But today it's a full category of products. And it actually doesn't require full rewrites. You can bring a serverless experience to containers and to Postgres, and basically what it generally means is auto-scaling and auto-healing of your deployment. And it's important because basically our belief is that it's going to supersede previous infrastructure technologies. And it's not like our own saying, it's something that like repeats over the last 20 years in the sense that every 5 years you have a major change in infrastructure technologies. So in the 2000s, people were racking servers mostly. We moved to virtual infrastructure, to IaaS. Kubernetes took a big portion of like the standard of deployment. And our belief is that the next generation is serverless. And it's not necessarily going to be us, it's just like a set of technologies which are going to bring this serverless experience. And this is actually also highlighted more or less by the CNCF. So in 2021, they highlighted that Kubernetes is actually disappearing for most organizations, and it's going under the hood in a similar fashion to Linux. It means basically that it's not disappearing as a technology, it's just like it's going to be used by less people, and most people are not going to be even aware that Kubernetes is under it, under the infrastructure. So now, if we briefly look at the history of automation and orchestration, there is like also changes, my feeling and what I saw is that like it went from Perl to Ruby to Python and to Go. And so actually here I have a question for you all. Who has more than 15 years of experience here? Huh. Okay, so I might need your help because I was looking I was looking for specific technologies from more than 15 years ago, and you'll see after, but I might need some help to fill the next slide. Who has less than 5 years of experience, professional experience? Okay, so you might have ideas of what will come next, because it's also coming from young generations. So what we see is that basically system languages are changing also, and they are usually working in pairs. So you have one technology that is used for automation and orchestration, and another set of technologies and languages which are used for high performance and distributed systems. And I have a few examples which are coming up. In the 2000s, basically the main languages which were used were Perl and C. Even the orchestration software were partly written in C, like CF Engine. And then the logos below are Nginx, Postgres, and MySQL, which were actually written partly in the 90s for Postgres and MySQL. And there were like the high performance side of it. And that's where actually I was looking for open source projects in Perl, and I struggled because in fact, Perl was massively used and is probably like still in a lot of code bases. But I didn't find any like large-scale open source projects which survived over time. So if you have any in mind, please let me know. I would love to add it there. But system administrators, as they were called at the time, were mostly using Perl for automation. In 2005, there was like an emergence of automation in Ruby. So two famous projects which were created at this time were Chef and Puppets between 2005 and 2010. And actually, if you look at a bunch of infrastructure companies which were created around this time, they started in Ruby. In 2010, there is for me two sides, like Python for the automation and Java for the high-performance distributed systems. So OpenStack is a famous one, which was written in Python, and SoulStack are also automations, and Ansible are also automation software. SoulStack didn't really survive. I mean, it's still running, but it's like getting less traction. Ansible still has traction. And on the high-performance side, you have Elasticsearch and Cassandra, which made it through time. And now, if you look at today, basically in the last 10 years, the main two languages are Go, and back in 2015, you started seeing the emergence or re-emergence of C++ projects, which were slowly superseded by a Rust project. Most like new projects for distributed system are written in Rust. I mean, this might be up to debate because we probably don't have enough history to see which one will survive in 2 to 5 years. In 2015, you have like Docker, Kubernetes, Nomads, and all the actually HashiCorp tooling, including Terraform, which is written in GoLab. And on the other hand, you have high-performance system like Envoy. The other one is ScyllaDB, that is nearby, ClickHouse, which are all written in C++. On the right side, on what is like now, Kuma is we'll speak about it later. It's basically a control plane for service mesh, and Loki is also written in Go. And on the bottom, you have Firecracker, Melisearch, and QuickWit, which are high-performance system and written in Rust. And so here, I mean, to me, there is a question on what is next. If you look at this, Go already has a long history, so there is some technologies which are getting over time, like C and C++, but to be clear, there is a question on how long it's going to be. Maybe there is going to be core evolution to Go, but I would not be 100% confident that in 2030 it's still going to be Go. And yeah, there is also some attempt to change in other like categories of languages. So Erlang is moving to Elixir slowly, C to Zig, and C++ there is Carbon. I don't know if any of this project will survive or get a lot of traction over time, but it's an important question to make sure that we don't stay grounded into some belief that this will survive over time, as is. All right. Now let's dive into how basically we are building this platform in Go. To give you some additional context, so we're abstracting a bunch of functionalities. We'll not go over all of them in details because it would be too long. We're abstracting cloud providers. We're also taking care of the build system. So we're building your application from a repository. And we're deploying across several locations, so we're global. We're providing a service mesh. Here I have a question again for you all. What is like, who knows what is a service mesh? Okay, it's a fair share. So it's actually an interesting technology. It's designed to simplify networking, and I would say it provides completely managed like layer 7 networking feature. We'll dive a bit into what it does exactly, but it's like emerging since 5 years, and it doesn't seem to be getting knowledge, or maybe because it's actually too transparent on a day-to-day basis. But we'll dive into how this is working just after. And we are also taking care of orchestration, some monitoring with basic logging features, and some storage capabilities. And when we designed the platform, we were aiming for basically fast builds and execution. So one thing we are trying to provide is a way where when you build locally and you push, it's as fast, so that like your laptop is not slower, is not faster than your cloud infrastructure, which does happen in a lot of cases with mainstream cloud service providers, simply because they are recycling old hardware. So that's one of the key goals we have. We're aiming for global deployments. We need, as a cloud service provider, to take care of multi-tenancy because we're hosting several customers on one single machine. And we're also aiming to build something which is scalable because we're not aiming to be a niche player, but we're actually more looking into deploying tens of thousands of apps. So the first question is what is the right technology? And when we designed, we saw 4 key possible abstraction layers. So the first one is building on top of cloud provider primitives. You have a lot of new platforms which are basically built on top of AWS or GCP, just because they are providing high-level primitives, so you can focus on packaging. But you are limited by the choice of the cloud service provider. And you are also limited by their structural costs because they want to do margin. The second option is to deploy on top of Kubernetes. It's also a fairly common choice. Third one is to build something completely purpose-built. And the final one is doing everything. It's like racking our own infrastructure, building the software, and doing everything. We didn't pick the fourth one, to be clear. We did this in the past. It's super annoying to deal with logistics and deploying servers everywhere around the world. We rolled out the cloud provider primitives option basically because, of margins and limitations this would incur in our own product. So we started actually with the Kubernetes option. But we ended up building our own stack because we had trouble into basically extending Kubernetes the way we wanted, to put it simply. So the stack today is containers which are running inside of micro VMs on top of BareMetal servers. And on the left side, you see Nomad, which we mentioned before, which is used for the container orchestration side. For the virtualization side, we rely on Firecracker. And on the networking side and for the service mesh and discovery, we rely on Kuma and Envoy. And it's all running on different BareMetal providers, depending on the location. And so here, the thing I want to mention is so we picked Nomad. We started with Kubernetes, and we migrated from Kubernetes to Nomad. The main reason is that we found it easier to maintain and extend because otherwise we would have had to play catch up with Kubernetes basically, and actually fight against a large open source community, which is a fairly large project where we don't need everything. So we went with Nomad because we believe it's simpler to use, and it actually provides multi-region capabilities out of the box. And so it's written in GoLang with a fairly small footprint, and it's easily scalable. So on the virtualization side, as we require multi-tenant security, we went with something which was open sourced by AWS, which is called Firecracker. So if you're familiar with virtualization, it's based on KVM, which is what is used by most cloud service providers for full-fledged virtual machines, like EC2 is running on KVM, DigitalOcean Droplets are running on KVM. But it's actually a slimmed-down version to make it more performant and have a lower surface of attack. So it's not doing orchestration, it's really purely the virtualization, and it's actually written in Rust. On the networking side, we rely on a technology called Kuma, which has been open sourced by Kong. It's also written in Go, and it's actually orchestrating a fleet on Envoy proxies, which are written in C++. And what it provides, and that's like what our service mesh is providing. It's providing like native encryption. So wherever like your services are deployed, the communication is going to be automatically encrypted so that you don't have to deal with security inside of the application. It's also providing like automatic DNS provisioning and native layer 7 load balancing, so that like, and it's actually providing way more if you dive into the feature of our service mesh, like retry capabilities, policies, ACLs, which we are not necessarily exposing today. And the end game is to move all of this concern to the infrastructure layer instead of the application layer. So that's what it looks like at the end. It's really a simplified version on the orchestration side. So on the left, you have what we call the control plane. So it's our APIs written in Golang, which are talking to main Nomad server. And we're actually orchestrating on the data plane side containers, which are running inside of micro VMs. And for each micro VMs, you have the mesh network on the side, and they are running on top of hypervisors, which are CoreOS hypervisors. And Kuma is doing the same thing as Nomad on the service mesh control plane side. So it's basically orchestrating the configuration on Envoy sidecar proxies. So inside of the control plane, you have a Kuma instance, which is actually dispatching configuration to all Envoy sidecar proxies, which are dealing with the production traffic. And so that's where you get all of it at the same time. It's the same, more or less the same view. So on the left side, you have the control plane. And on the right side, you have what we call the data plane. So it's where end user and our users' workloads are running. So if you go from the top left, from the user on the top left, basically it was us using the CLI just before, which is written in Golang, and actually like most of the tooling that you might use is written in Golang. So if you use Terraform, it's going to be written also in Golang. And it's actually performing REST calls to our own APIs, which then we have a gateway which are translating as a REST call to gRPC, because all our internal APIs are written talking gRPC. A Postgres database, and we have a bunch of workers written in Golang which are pulling orders and actually dispatching them to Kuma and Nomad to propagate the configuration. And on the right side, you have, we see actually the kind of the critical path, because on the left side, we require performance to boot fast the traffic, but on the right side, it's where actually like you have the customer traffic. So if you go to a public URL, and the load balancer is Envoy, which is written in C++. It's configured by Kuma. And for each micro VM, you have a sidecar which is processing the traffic, which is again C++, and the micro VM is in Rust. So you see exactly this division of like Golang for automation and scaling like the configuration part, and high performance on the right with Rust and C++. So we have 6 core locations and 250 edge locations. And if you remember before, we deployed 2 services across 6 locations and 3 contents. So we'll check if they are actually working. If we go here, your service is almost ready. So this is not expected. That's the amazing thing of doing a live demo. Huh. So that's you. Yeah, that's like perfectly not what I was expecting. Okay. So you saw it working, and now it's not anymore working?
I saw hello world and also that the global was the IP address I was getting at location.
Yeah.
But now it's back in like its stage.
That's interesting and not at all expected. Thank you for troubleshooting our platform today. Okay. Huh. That's interesting. So that's more what I wanted to see. So it seems like for whatever reason, yeah, if you saw it running, okay, so either it's load balanced to something which is not working correctly. That's the magic of a distributed system, because actually we see all the instances which we just deployed before, which are running, and they are running since 11:10, so for 20 minutes already. With the instance, so yeah, that's interesting. I will we'll dive into, we'll explore this, and actually there is also some magic happening here because for whatever reason we're going through the edge location which is in Paris. So, and that's the magic of networking. I was testing it on my phone earlier, and we were going through another edge location, which was actually, I think, in Germany. And from my Airbnb, I was going through Milan. So depending on, so that's a fun networking part. Yeah, interesting. So anyway, this is globally distributed and an interesting result, which was not fully expected because both our apps are actively running, and so we're providing all the global networking layer. And so yeah, this is our Next.js app. So yeah, interesting. And actually, like this fun networking results is my last mention. So that's what I had this morning from an Airbnb here. The edge location is in Milan, which makes more sense. There is probably no edge part in POP in Florence, and the core location is Frankfurt. But actually it depends on the ISP, and that's where we have less control because it's going into business agreements on where the cheapest bandwidth is. So you might have things which makes no sense at all, and where it's getting out of our control. And I'll briefly explain this after. On what we just saw, the 6 locations, actually before we were highlighting all the APIs in one single cluster. It's not true, because otherwise we would have one single cluster for the whole world. We actually have one Kubernetes cluster, and that's the fun part. We're using both Kubernetes and Nomad. So Nomad is used for the lightweight orchestration on the hypervisor, but our own stack is deployed on top of Kubernetes. And so on each continent, so we are present in North America, Europe, and Asia. We have a Kubernetes cluster, and each of this cluster is responsible for deploying in all the data centers on the continent. So the flow is actually, we are taking care ourselves of dispatching the orders into each continental cluster. So that's why you see the worker which is located into the global cluster, which is actually dispatching orders into each continental cluster responsible for each data center. And there is a global load balancer layer, which is separate from all of this because this is really the provisioning part. And this works this way, actually. That's so here you have on the left the end user request. So if you go right now to global-golab.coab.app, you're performing. It's going to perform a DNS request, which is resolving to an Anycast IP. So, is anyone familiar with what is an Anycast? Okay, so Anycast is simply the principle of announcing one single IPs through multiple providers. So I can have one IPv4 and one IPv6 and announce it from different locations through the main internet protocol, which is BGP. And so basically the same IP is announced right now in New York and in here to reach the edge network. And this is where the politics and the internet part comes into play, because it might happen that it's cheaper to go through a lot of kilometers and not go through the shortest path. And so, yeah, basically when you type your URL, you have one single unicasted IP. It's going to go through the edge network. The edge network is going to terminate the TLS connection. It's going to deal with HTTP3 if your browser supports it. It's going to provide caching, and from the edge network, we are actually going to route to the nearest core location, and we are going to transport the traffic to where your application is actually running. So if you deploy, for instance, only in New York, it's going to go through the nearest edge location, nearest core location, and then to actually where your application is running. And that's it for today.
Thank you, Yann. Okay, so let's move to the questions. Any question about this talk?
Hi, thanks for the talk. And so, are you taking care of the deployment building phase stage? How does it work, and what languages are supported using build packs or other technologies?
Yeah. So we're, if you look at this diagram, like the first thing when we provision is going to build. And so we're actually going to provision like micro VMs for the build phase. And inside of the build phase, we're using build packs, and we're also building like from Docker files. So depending, and so here the key thing is to try to make it as transparent as possible. So I mean, build packs have limitation, but yeah. So, and that's what enables us to support application in the same fashion without having you to rewrite them.
Okay. Any other question?
Hi, great talk. Sorry. Just a quick question. You use Kuma for your service meshes.
Yeah.
Why not Istio, or what's the benefit, downsides? So just in regards to that.
Yeah. So the reason you started using Kuma is actually for the multi-region capability originally. Istio does have it, I think, but it's like an enterprise version. And as a small startup, we couldn't really pay for it. So the main driver for using Kuma is this. And actually, if I recall correctly, Istio is also provisioning envoy proxies. I'm not, yeah.
I think so.
I'm not completely sure anymore. I did a talk on this and then I forgot. But from what I recall, it's also using envoy proxies. So, and the key thing actually is that we're relatively flexible in removing Kuma in a way, because Kuma is using a Postgres database behind the scene. It's written in GoLang, and it's using the protocol envoy to dispatch configuration, which is XDS. And we actually already had to patch Kuma, because one of the specific of our job is that like all of these technologies are designed for companies where you usually have like one or I don't know 10 tenants. We have thousands of tenants, And so for each, because for each single customer, we are creating a dedicated tenant so that they don't see each other. And so it's the same in Kuma. So we have like thousands of tenants, and we are actually one of the largest users of Kuma in terms of tenants. Not necessarily in terms of like number of like proxies which are used, but the number of tenants is pretty unique. So yeah, and actually I think we have so we have a strong relationship with Kong, who is the creator of Kuma for this reason, because we have a pretty unique use case.
Okay, thank you. Just a follow-up, because I see it now. Use for your API calls gRPC. I assume that's because of performance?
On the public side, you mean?
Yeah.
So on the public side, it's Rust. So if you, and the reason, so we were thinking about like exposing directly gRPC. The main thing is like the browser support was not like necessarily crazy. So we have a gateway which is actually extremely annoying for us to maintain, which is translating the REST calls to gRPC calls. And actually we have like sometimes bad error propagation related to this. So it's not the best thing. Ideally, if we were able to expose gRPC, this would be easier for us to maintain. But on the other hand, like gRPC, if you want to do a simple curl or for a REST call, it's a bit less user-friendly also. So today we still have like REST API, and internally I would say we are using gRPC because it's only, we have several microservices, and so we are using the feature to have the, with the product bus and so on, to simplify communication between these microservices.
Thank you. I will maybe find you later and ask you a lot of questions.
Okay. Any other question? Yes, coming.
Hi. Thanks for the talk. So you said basically use Quick to get to the entry point of the architecture, and then it's downgraded to HTTP1, I believe. I was wondering if you can have HTTP2 end-to-end.
Yeah, we do. So you said Quick at the beginning? Yeah. So I mean, so we don't have HTTP3 end-to-end. So it's terminated at the edge location, but we do have HTTP2 end-to-end, and we need it to support gRPC application. And it's actually like we have a full blog post. So if you go to coyab.com/blog, we have like several engineering posts, and there is one explaining how we actually how we dealt with the implementation of HTTP2 end-to-end. Because you need to, I mean, due to the way negotiation works, you need to force the protocol. Otherwise, it's going to fall back to HTTP1 at some point, because the auto discovery mechanism are not good enough. So yeah, you can do, and actually one of the challenges, like, because we support also WebSockets, so we need to have like a long-running connection end-to-end. Otherwise, your WebSocket is going to constantly retry. So yeah, and so we're basically propagating the configuration into Envoy, so that like, and we're forcing it to HTTP2.
Okay, we still have a few more minutes in case you have any other question. Okay, I guess we're good. So thank you again, Mr. Leger. Okay.
Thank you.